Enquanto tá vermelhinho aqui, tá gravando.
Ah,
Ok.
legal.
No caso que eu falei a vídeo, eu não ajudo aí.
Pronto. Tem aqui também, aqui. Era 27 ou 2018? Isso. Aqui é 18. Ali é 24. Obrigado. Mas a gente tá aí, pelo menos. Então, obrigado. Vou gostar aqui. Nossa. Okay, so let's get started. So we reached halfway of the beautiful paper course. For me, for you, halfway is on Friday. So this will be the fourth paper. So today we'll be discussing Witten's paper on the large n limit. So it was a paper right after Tufts' paper from 79. Where he just discusses what we can learn about the strong force, about Baryons, about Mesons, Baryons, and Glueballs, just by drawing diagrams and counting powers of n to make some estimates of which processes are small, which processes are big, and how we should think of particle physics just based on that very qualitative but very general large n analysis. Okay? So, in particular, that's all that matters. So we are not going to be discussing space-time propagators for the most part, derivatives for the most part. It's only about drawing propagators and understanding what the large n counting matters. And the basic intuition is that because we have many degrees of freedom, typically physics simplifies when we have either very few degrees of freedom or sometimes when we have many degrees of freedom, and that's again a simplification. And in QCD, when we have quarks and gluons, we have many degrees of freedom, but many more gluons than quarks, because there are n quarks and n squared gluons. And that should lead to an important simplification. So the fact that there are many more gluons than quarks implies a ton of phenomenology, and that's what Witten discusses beautifully in this paper. Now this paper, I thought it was easy but long, so I cannot describe everything. So my goal is to describe the beginning of section 3, part of section 5, and then summarize with a discussion. And so that's what we would like to do. So Witten starts by claiming, not starts, but in section 3, or he does it before, but in section 3 he really wants to make this point, that based on large n you can conclude a few things about mesons. And for example, point 1 he says, mesons for large n are free, stable, and non-interacting. He continues, mesons, masses, have smooth limits for large n, and the number of mesons is infinite. So a ton of information, right? Mesons are free, they are stable, there are infinitely many, and their masses have a finite limit. Namely, it makes sense to ask what are the Meson masses. They could be 1.2, 1.7, 2.3, and they all have a limit when n goes to infinity. So it's a lot of information, so let's address that one. Okay? So point 1 is about mesons at infinite time. It's a bit hot, no? I'll turn on the air, that's okay. No, someone should. Can someone turn on the air? The remote is back there. Okay, mesons, why mesons at large n are stable and so on. Before, let me just remind you that there are three objects that we are going to discuss today. Mesons that are basically quark and anti-quark pairs, which in a picture you will draw as an open string between a quark and an anti-quark. Okay? And this object that will have the quantum numbers by this symbol, I mean it has the same quantum numbers as something like a Q bar acting on a Q, and there could be many gluon fields in between if you want, but this would have this type of quantum numbers. By this I mean that you act with this operator on the vacuum, and it will have overlap with the Meson state. It will also produce other stuff, but this is the type of quantum numbers that the Meson has. Then we have a Glueball. A Glueball would be thought of, if you want, in a string-like picture as kind of a closed string, and it will have the quantum numbers of something that is also neutral in color, that also doesn't transform, but something like trace of a to the 4, for example. So you see that here we have a beginning and an end, and then a product of matrices. So this is a vector, this is a vector, and these are matrices, right? And under gauge transformations, this transforms from the left, this from the right, and these guys are conjugated, so this is gauge invariant. This is also gauge invariant, but this is a closed object, it's a trace. That's right, it's a problem, A, and then we take a trace, and then it would be a Glueball. And then we have Baryons. And Baryons, they have an important difference compared to Mesons and Glueballs, which is the picture we are going to draw would have to depend on n. For SU3, Baryons have 3 quarks, because out of 3 quarks I make a singlet. For SU4, I will need 4 quarks, right? And so Meson, in a string-like picture, would be something like some kind of string-like junction, where I would have n quarks, and this would have the quantum number of something like a bunch of quarks, where I would multiply n quarks, and this would be an object that would have overlap with the vector. Okay? Okay, so this is very schematic, but it's just so that we know the notation of what we are describing. Baryons, they have n quarks. These are all quark lines, they are not gluons. They are, I have a bunch of quarks. Glueballs, I have a neutral state without quarks. Mesons, I have a quark and anti-quark. And in nature, you could imagine other objects like exotics, like states made up of 4 quarks, for example, and so on. And one of the claims is that at large n they don't exist, for example. That's one of the points we even will discuss, is that exotics, like quark bar and quark bar, don't exist at large n. Only these things exist. Okay? So let's start with mesons that are generated by this type of states. And then we think of them as heating the vacuum with a current of the form Q bar Q. It could be Q bar Q with some gamma matrix in the middle or something, but that's not important. From the point of view of color, we act on the vacuum with this state, which I draw like this. I have a line, and I have a quark getting out, and an anti-quark getting in. And then, if I want to study mesons, I could ask, for example, for the 2-point function of these mesons, of this operator that is created by this meson. And now, we could start drawing things like, for example, an exchange of a gluon between these two. This gluon would exchange here, and so on. And it would also, let's do it like this, exchange here. We will draw a diagram like this. And now, let me actually make the following. Let's draw this. Let's draw something a bit funny, just to become clear in the second line, like this. be a diagram that we could draw. And as Meson explains, he counts diagrams like this. He says that any cubic coupling that you have here, he attaches a coupling 1 over square root of n, and some coupling g, but g I will not keep track of. So for example, in this diagram, let's see how many vertices we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Did I forget any? Please help me. I probably forgot one. There is one up here. 12. So this diagram will contain 1 over square root of n to the power 12. And then, what is the flavor that's flowing here in the middle? What's the color that's flowing here? It could be any color that's flowing here. And therefore, each of these faces gives me a power of n. And we have, let's see, 1, 2, 3, 4, 5, 6, 7. And so we would have n to the 7, and therefore n. And you see that this is the same scaling as just the tree diagram. The tree diagram was also just a single power of n. All these diagrams that you draw on the plane, they scale like n. They have vertices that suppress in n, loops that enhance in n, and they combine nicely, and in the planar limit at large n, these diagrams survive. What diagrams don't survive? Diagrams that will be non-planar. A diagram where I will draw a propagator from this line to say this line here. Because I would add vertices that suppress, and I destroy many color loops. Now if I follow the color loops, they will not be suppressed. Okay. And so, all these diagrams are planar, so that's the key thing. In the large N, I only draw planar stuff. And now, we can ask, when I have a planar graph, what happens when I cut the planar graph to see what is flowing, what is being generated? And you see that as you cut to see what state is being generated, and you follow these lines, what do we see? We see a quark, then we see a gluon, then we see another gluon, and then we see a quark. Moreover, this index of the quark is in the same loop, so this index of the quark is the same as the first index of the gluon. The second index of the gluon is the same as the first of the next gluon, and so on. And so what we are seeing here in the middle is nothing but the state of the form that we described before, Q bar, then gluon, and then Q. And so all intermediate states, they are all Mesons. We could have complicated planar graph, but it's a disk. And because it's a disk, when I cut, I have two open ends. Right? It's just cutting a disk, it will give me a Meson. Now, let me open a parenthesis and let's repeat the analysis for glue. Wheaton does it at the end, but let's do it now. Let's think of the same analysis now for a glue ball. So let's imagine that I draw now an operator that will generate a glue ball. So it's not a quark anti-quark here, but I'll put an operator that is a closed string. So it could be, for example, something like this. I emit a gluon, I emit another gluon, and I emit the last gluon. So 3 gluons, for example. So you see that this operator is A times A times A. If you follow the index, right, this index is the same as this. This index is the same as this. This index is the same as the last one. So this is a picture for trace of A times A times A. Right? Do you agree? From the point of view of color, if you follow the color, this is A times A times A. And now I draw a graph going, and these guys will do a bunch of things. They will exchange some gluons. This will exchange some more gluons here. And then I go to the glue ball again, I close, and I go again to A times A times A. And now you see that this guy has the topology of a cylinder. So whereas this was a disk, this is a cylinder. Right? This is a cylinder topology. Do you agree? And now we could also count powers of n if we want. Okay, why don't we do it? Let's do it. Let's count powers of n, and let's see that we have 1 vertex, 2 vertices, 3 vertices, 4, 5, 6, 7, 8, 9, 10. So 1 over square root of n to the power 10 times loops of color. Let's write them down. 1, 2, 3, 4, and the outer one 5 times n to the 5, and this would be n to the 0. And you can easily see that the trivial propagation is also n to the 0, so that's the scaling of all planar graphs. That's how they are normalized. Okay? And so we have this diagram, the cylinder, that will describe the Glueball going from here to here. And we have the disk that describes the Meson propagation. And if I cut this diagram, same story, I cut it, doesn't matter where I cut, what do I get? For example, a gluon times a gluon times a gluon times a gluon. And I say times because you see that this index is the seventh disk, and then this index is the seventh disk, and this index is the seventh disk, and so on. So what I'm seeing here when I cut is not the same Glueball, it's another Glueball, it's A. But fine, it's a Glueball. So that means that this operator acting on the vacuum produces all sorts of Glueball states, but just Glueball states. This state, acting on the vacuum, produces all sorts of Meson states, but only Meson states. Right? So I have a disk, I have a disk. I cut, I get a message. I have a cylinder, I cut, I get a closed string. Right? I don't get other things. But I can get many types of closed strings, and I can get many types of open strings when I cut. Right? And so we conclude that this picture here should be interpreted as a sum over the probability for creating the Meson n divided by, if we did it in position space, something like k squared plus the mass squared of Meson n. Right? We just interpret that two-point function. We cut, we have some kind of Riemann decomposition. And we would interpret like this. And similar picture here, we would say that this is the sum of the probability of creating Glueball n over k squared plus the mass squared of the Glueball n. Right? And that's the only thing that could happen. Now, let's see, and here we would say that this Bn, for example, you would interpret it as the probability of creating blue state n and annihilating it, so you would call it probability squared, because you create and annihilate. And in this case, you would say this guy is of order 1. That just means that this operator generates with order 1 the Glueball. And this one, you would conclude that this is the probability of creating the Glueball squared, and this gamma scales like square root of n, because the full result scales like n. Right? And so I act with the Meson state, and I produce with amplitude square root of n one of the nth Mesons. Right? And so this, of course, I can write this as, I can say that this is n times some a tilde, where a tilde I just took out n, and then this has a finite limit. This is n independent. And because it's n independent, these masses are n independent. They have a good limit. First thing we proved. Second thing we established is that there are infinitely many. Why? That's because we know that this correlation function, when k is very big, should behave logarithmically. That's asymptotic freedom. But you cannot get a log if you sum 5 terms. Then it will decay as 1 over k squared. So we also conclude there are infinitely many Mesons. Okay, so we learned that as Argent there are infinitely many Mesons. We learned that we can produce them through this QQ bar operator. We learned that these Mesons, okay, and that's one of the things we learned. So what we learned now already was infinitely many. The mass at n equal to infinity exists. This makes sense. And we learned that this probability of creating this amplitude for creating these gluons is scales like that. Okay. Now let me emphasize that this is really at infinite n. Let's see something we could do here. I have this cylinder, right? It's a cylinder. And now you could do something like you do as kids when you cut paper and glue. You could call this stuff here alpha, this stuff here beta, and you take this cylinder and you could imagine gluing it here. Let's put alpha here. There's a loop here, so I will replace this loop by alpha. And this n, let me replace this loop by beta. Okay, so now imagine you have the planar diagram, but now there's a cylinder coming from here, going up here and going to beta. Right? What will happen now if we cut the diagram? Now if we cut the diagram, this cut, that before we were getting this, now we will get q bar a q times the trace of a to the 4. So what will we see now? We see that now there will be a Meson and a Glueball. Okay? But now it's non-planar, because now I cannot draw it on the plane. I have manifested this cylinder here. Okay? So what we would conclude is that this correlation function here would behave like n. But then there is a correction. It was 1 over n compared to this n, so 1 over n squared difference from the two. And now we would have production of, say, a Baryon and a Glueball. Whereas this diagram here, this leading one, if I were to draw it, I would say I produce a Baryon, a Meson, and I annihilate it. And so you see that at finite and then at higher powers in n, you get more and more things. Now you could get a Baryon, you could even get more Baryons, and so on. But at planar level, you only see Baryons. You only see Meson. Now, for example, you could not claim that you only have poles. Now you have two particles flowing. Now you have cuts. Now it's more complicated. You will get cuts, the K dependence will be less trivial. Now we could not argue that you need infinitely many and so on. And that's fine, that's the real world. In the real world, we don't claim that we have infinitely many particles, many become resonances and so on, and that's totally fine. Okay? Anyway, we take large n, so we drop this contribution. Sorry.
Why it is 1 over n coefficient?
Because it's non-planar. Non-planar graphs are much smaller than planar graphs.
Yeah, then it surprised me because here it is n, but in the cylinder you got n to the 0. Why they don't differ by 2?
Because we have a loop here and we have a loop here, so we have 2 powers of n. And now I replace those powers of n that I don't get anymore and put the cylinder that we saw is over 1. So I lost 2 powers of n and replaced by something over 1. And therefore I got down by 2 powers of n. Okay, and this is all fine, that all makes sense, right? If I have an open string propagating from one point to the other, the open string is the Meson. Of course, there is a chance that this open string could emit a closed string that could propagate, but this is suppressed in genus, and this would be the origin of the 1 over n squared. And then it could emit through Glueballs, etc. But these processes are all suppressed, and we drop them when n goes to infinity. What else do we drop? We drop, for example, the diagram where this line is omitted. What this line being omitted? This line being omitted would mean that I have a quark here, an empty quark, instead of a glue one. This diagram exists as well. It's a vertex where it's the Yukawa, not Yukawa, but it's QQ bar and A. Right? So this exists. But here, what happens when I will cut a diagram like this? Let's cut a more beautiful one. You see, what happens when I cut a diagram like this? I get a QQ bar, and here I get a QA bar. Right? So I get a state that has 2 quarks and 2 antiquarks when I cut this. So this would be one of those exotics that have more quarks. So here, this we could call it something like an exotic. It's something that would have a QQ bar and then a QA bar. Right? And what we see is that this is suppressed at large angle. Okay? So that's another prediction, which is there are no exotics. Okay, but let's maybe address the most important one that we mentioned, which is that mesons are free. Let's recall why they are free. This we did not establish yet. What does it mean to be free? It means that the interactions are small. So now we need to consider interactions. So far we only described propagation of meson and propagation of Glueballs. Now we have to describe interactions of mesons and of Glueballs and of Baryons. Any questions so far?
Yeah, I have another one.
Yes?
The Mn in the large n limit exists. Is it too quick to draw the conclusion by this formula?
No.
Because you
Why would it
do a specific loop diagram calculation, and you draw the conclusion that it has a finite limit. Is this what you are doing?
No. So what we conclude is that the summation of all planar diagrams comes with a factor of n in front. N only appears in front.
Yes.
I also conclude that I have a summation over everything that can flow, and what can flow I see are just mesons. So I also know that this is the structure of what is flowing.
Yeah, but how to tell this is exactly the structure? No, there is no other very weird stuff.
That's confinement. It's the statement that if it's neutral, it must be one of the particles of the theory, and from quantum numbers it's a meson. Anyway, this is it's a summary of the paper, and I know that you did not read the paper before, but everyone else, most of the students did, so I cannot slow down so much. So
We can talk about it.
you can ask later, but let's give priority to questions from the students. So any other question?
So at small n, you should have not just single particles, but a multi-particle continuum and bound states exchange, right?
That's right.
What's the difference between them?
So the key difference, so what's this again? What do we expect in the complex k-square plane for a two-point function? In a physical theory, here is what you expect. You expect a cut for multi-particles and poles for the bound states. And that's what you expect. Bound states or stable particles need poles. And then there is a cut starting at 2 particles at energy equal to 2. Then, if you went through the cut, you would see that on the other sheet there would be poles, and this would be resonances. Then, you can think that when n goes to infinity, this multi-particle cut is disappearing, and these resonances are going to the real line, and we get infinitely many stable particles.
These exotics, are they more like a bound state or more like multi-particle?
The bounds, if they exist, they are resonances. They are resonances. I mean, particle physics is democratic. I think this distinction between bound state and fundamental, it's our language. They are just poles in the, they are complex poles in the two-point function or in the n-point function. Okay. Anyway, large n, you see, what we are trying to explain is a bunch of phenomenology at large n, and then there are two ways of seeing this. Because this is actually how nature works more or less, the way we assess it, nature does this more or less. Nature, mesons are more or less free, their ability is very small, and so on. So this is evidence for the validity of large n. You could use the other argument. You could say, let me use large n to predict things about nature. That would be a bit hand-waving, because we don't know exactly what's the parameter. Is it 1 over n, or is it 4 pi over n, or is it 1 over 4 pi times n? It depends, right? So where you put the pi's could mean that large n could be a loss of approximation or could be terrible. And he says, even that nature behaves more or less like all the 9 predictions we make. For example, exotics are not very common, right? They're very hard, they're not very relevant for most phenomenology. And that's a prediction of large n. Mesons are free, and that's a prediction of large n. There are many mesons. Not infinite, there are many. That's a prediction of large n. And so on. So that's kind of an indication that large n is not that big. Right? But the direction that Witten argues is that let's use nature to argue that probably large n is not such a bad approximation.
The fact that the propagator does not have only have mesons, for instance, propagator of mesons only have mesons. Is it sufficient to conclude that there is no interaction?
No. That's not sufficient. That's what we are going to do now.
So at some point it says to argue that the poles are real.
Sorry, let me say different. It's almost sufficient. Because if mesons were not free, it would mean that when you have we are saying that the propagator would just have mesons propagating, right? But if they were not free, that would mean that their coupling would not be small. Then you would immediately have 2 mesons propagating. So yes, it's related. The fact that the one particle propagator of meson contains only mesons and nothing else. For example, it doesn't contain the meson plus a Glueball. This would be a Glueball. This is not there. The fact that this is not there, and only this is there, is indicating that the mesons are basically free. They create the mesons and they propagate, but they don't split, they don't join, they don't interact with other stuff.
It's not a null.
No, it's more or less enough. Now I'm taking it. It's more or less enough. But we are going to argue based on a slightly stronger observable that makes it obvious. But already the fact that the propagator of mesons decouples from the rest is an indication that they are free. Yeah.
So when he argues that the poles in the current two-point function are real, he says that this must be so because otherwise it would violate the spectral representation. Don't understand this.
Yeah, it's a statement that you act with a J on the vacuum, and you get a summation over states n with an amplitude an, right? And these are states of real energy, and therefore when you Fourier transform to write in Fourier, they are poles at real positions. It's just the fact that these are physical states. It's not more than that. Any other questions? Okay. So, what does it mean that mesons are free? Or that Baryons and the row and so on, that they are approximately free? So that means that when I send 2 mesons at each other, that the free propagation is much bigger than the interaction. Right? Or, you could also say, another way of saying that's related is saying that the 3-point functions, for example, are much smaller than 1. And all these interaction vertices are very small. And that is just a statement that correlation functions are suppressed or factorized. So for example, the correlation function, or you create a Meson here, you create another Meson here, and you annihilate the Meson here. And now we decorate it with all sorts of gluons, but in a planar way. Now I'm not drawing double line notation just for simplicity, but I draw something like this. Then you easily see that this diagram is of order n. Why? Because the one without gluons is obviously order n. I just do a loop. And then we said that planar stuff doesn't change, so it's also of order n. You can also see that the empty one is of order n, and when you put a gluon, you get two faces and 2 powers of 1 over square root of n, and so nothing changes. And now you can recursively add more propagators, and each time you have a propagator, you break the face into 2, but you get 2 vertices, and therefore nothing changes. And so it scales like n. But this n, we have to be careful, because this n, I should interpret as there was a probability of creating this guy that was square root of n, probability of creating this guy that was square root of n, and probability of creating this guy that was square root of n. In other words, this n, I have to say, is square root of n to the power 3 times 1 over square root of n, where this is the interaction between my 3 methods. In other words, if I normalize the 2-point function to 1, this is what I would claim the 3-point function is. And then the basic statement is that this goes to 0. And similarly, the 4-point function, you would conclude that the pi and pi and pi and interaction scale like 1 over n, and therefore this goes to 0. And therefore, just based on large n analysis, you conclude that Mesons are free. They don't interact that much. Let me see if I forgot something that I think is quite important. There's something more, actually. You could ask, what happens when I cut this diagram? Right? And when you cut this diagram, you could, for example, cut it here. And what happens when you cut here? What do you get? You get a Meson, quark, anti-quark, and a bunch of gluons. But you could also cut it here. What happens when you cut it here? You get 2 Mesons. Right? So depending on how you cut it, the same diagram could contain 1 Meson or 2 Mesons, or you could be able to separate and get Mesons. So in total, he concludes that if this momentum is P, if this is K, and if this is Q, he concludes that in general, you could imagine terms of the form 1 over P squared plus M1 squared, 1 over Q squared plus another Meson squared, times 1 over Q squared plus M3 squared, where by M1, M2, M3 I mean the various ions that you would get. Or you could get terms with just 2 propagators, but you would get all these possible types of structures. And this would interpret precisely as the interaction vertex between the gluons. But then he points out that once you are going to draw higher quark diagrams, the same subdiagrams will be there. So it's not just that I get 3-level-like objects. By 3-level I mean you cut things and you don't increase the number of stuff that you are putting in. But also I get 3-level objects where when I draw a 4-point amplitude, this 4-point amplitude could contain a genuine contact interaction, but also some interactions with 3 points that I computed before. And these guys were known before. And this is very important. So the claim then is that what we get basically is the claim that there exists a Lagrangian for the pion. The pions are free, so this Lagrangian is roughly kinetic term, Okay, I'm setting in this lecture, of course, derivatives are equal to pi. But pi is not pi. So we have a kinetic term, and then we have plus 1 over square root of n times a cubic pion vertex. And by cubic pion, of course, there are other fields. There is also 2 pions and 1 rho, which is just another meson. Right? When I write this, I mean all the mesons. Pi square, rho square, all the possible mesons. And then all cubic interactions. And then there is some contact interaction, 1 over n times some, for example, pi square, rho square, plus, etc. So that's what large n tells us. There is some pi at Lagrange with infinitely many mesons and interactions that are more and more suppressed, such that when n goes to infinity, I just get a free theory of mesons. Okay, each of them with their own mass, right? So there is d pi squared plus m1 pi squared, etc., etc.
I'm not sure if I understand this argument about factorization of the orbital points. Why does having multiple poles imply that you can factorize the pole?
It's just a question of basically what's the difference between diagrammatics and Lagrangian, and there's no difference, right? Lagrangian is just a place. If you give me diagrams, and if the diagrams come with the right symmetry factors, a Lagrangian is just a bookkeeping way of putting them in a simple formula that generates all the graphs automatically. And because all our arguments are graph based, he's just saying that it follows from the exponential of a Lagrangian. It just means, for example, it's connected things come out, the counting comes out right because it's in the exponent and so on.
No, I don't understand the Lagrangian connection. What I don't understand is the factorization of the 4 points into 4 and 3.
It's just a statement that in the 4-point function, there are diagrams like this. You just take this 4-point function and you draw something like this, which is similar to this, and then something in the bottom the same. And so in the 4-point function of 4 mesons, you have things like look like that. There's the mesons here. So, but this is an object that is not, so you say that this object, I compute once, the full planar graph. And I subtract the cubic stuff. Whatever remains, I define that to be the quartic interaction. You see, so you compute the full thing. That's what you compute. When you do a planar graph, when you sum over all diagonals inside here, you are computing the full thing. Now I want to write the full thing, I want to promote it to a Lagrangian. I cannot put the full thing in the pi to the 4th. That would be wrong. Because then I will generate terms from 2 cubics that would be not there. You see? So if you give me the 4-point function and I want to construct a Lagrangian, I have to write your 4-point interaction as I have to subtract what you get from 3 points to see inside there what is genuinely new. No, 3 points is the minimum count. Okay, so we learned that pions are free. You will also learn that Glueballs the same story. If I have Glueballs, they mostly scatter and touch. Gluons and pions, they mostly, so this is also true if one of them is a gluon. They prefer to be independent and not to scatter with each other. If you have 2 Glueballs, the same thing is true. The Glueballs are also prefer to go and touch. And so, free, and so the story is similar for Glueballs. Which again explains why it's so hard to see Glueballs. They decouple, so it's not like we saw many Glueballs. Okay. Any question about this? So this I think would be the main things. Let's see. What else physics does it point out in the beginning of section 2? So first point, we already did everything. Mesons at large n are free, stable, and non-interactive. Meson masses have a smooth limit for large n. Number of mesons is infinite. Okay. Point 1. I don't know how much time passed, but that was point 1 on page 67. Point 2. Meson decay amplitudes are of order 1 over square root of n. That's this statement here. Meson elastic scattering is of order 1 over n. That's this statement here. And are given by a sum of 3 diagrams. That's the statement here. More generally, Meson physics in a large n limit is described by the 3 diagrams of an effective local Lagrangian with local vertices, blah blah blah. That's what's happening. Then point 3, Zig's rule is exact, meaning singular octet mixing and mixing of mesons with blue states is suppressed. That's what we saw here with this coupling. Mesons for large n are pure QQ bar states, no mixing, for example, with QQ, Q bar exotics. That's what we also saw there. Okay? So we went through all the physics points in this section 3. Now, we could imagine baryons. Also very important object, like the proton. And now, this could be a proton. Okay? Do we have the same thing? No. It's not true. It's wrong. Baryons are not free. Baryons, if I send 2 baryons, it's not much smaller, it's not much bigger than the interaction of the baryons. That is just not true. Okay? So for baryons, we have to retain things. So baryons is a bit more subtle, and so that's what is very cute about. Now we turn to baryons. Before, let me just make a comment that once you have a Lagrangian like this, you can rescale the field pi by n, by square root of n. Let's see what happens when I rescale the field by square root of n. Something beautiful happens if I rescale all field by square root of n. This Lagrangian becomes n times a Lagrangian for a bunch of pi tildes, rho tildes, etc., where there is no n dependence. Do you see? If I rescale by square root of n, this becomes n times this. This becomes, it cancels this, and it becomes n times pi tilde cube, and so on. So this is true. Okay? So that's something usual in quantum field theory. When you write a Lagrangian, which has pi tilde square plus pi tilde cube plus etc., and n is in front, you should think that these are small interactions. It's just that you chose a normalization to put the coupling in front. But it's a convenient normalization. So this thing, where all interactions are order 1, is the same as this, where it makes manifest that they are small and small. But it's the same story. So let's keep this in mind here. Okay, so
is this thing related to the statement about the masses being well defined?
about what, son?
About the masses being well defined and positive.
Well, here in this pi tilde, there will be a term in our group derivatives now, d pi tilde square plus m square pi tilde square. But you see that both, from the point of view of n, they are both quadratic. So this m and the m that appears here is the same. There's no rescaling of n, nothing. So mass is finite and it will just finite. It's not related to that. Okay. So now, variance. And now variance, there's something interesting going on, which is that, let's imagine the 2-point function. But now, the 2-point function, there are n quarks, right? So there are many lines. Okay, so that's very different from the Meson where I have 2 quarks. Now I have many. And now, we ask, what happens when I exchange a gluon between one line and one faraway line in a non-planar way? And so let's see. So we have 2 vertices, and so we get 1 over square root of n squared But now, because there are many legs to choose, there is a choice of the first leg, which is n, and the choice of the second leg, which is n. So in total, there is a factor of n. So it is not true that I only consider planar graphs. Right? You see, there is an enhancement because there's a big choice. Naively, it looks even worse. That if I consider now a two-loop diagram, I would say that now the two-loop diagram, this scale like n, there's another n, so the two loops naively scale like n squared, which you could be worried. Right? Because now it looks like one loop is n, the other is n squared, and now it's not like before, where all diagrams that were planar scaled in the same way. Let's note that, for example, this diagram here, which is another diagram at two loops, consider just this part here. Let's see that this part is also of order n like this one, and not n squared. Let's see why. Because we have 1 over square root of n for each of the vertices. And then we choose 3 legs to use, not 4. Right? Because one of the legs we use twice. And so this also scales like n. So what's the difference between these two diagrams and this one that scales with n squared? This two-loop diagram here. The difference is that this one is disconnected. This one uses 2 legs and 2 other totally independent legs. Right? And so what this smells is like something, like maybe what we have is something like e to the minus n times a nice function of the various parameters of the theory. This could be what's happening, and it is indeed what's happening. So if you had something like this, where this was something like a plus b times g squared times the coupling plus c times g to the 4. If something like this was happening, for example, this would be computing some energy, then there will be some time here, for example. When you would start expanding this in perturbation theory, you would start getting 1 plus n squared g squared. But you would have to resum. A bit like what we had to resum the logs to see what's the fate of the logs. Does it really become bigger and bigger? No. They just exponentiate like here. Right? And so the claim is that Baryons, for example, if I compute the 2-point function, meaning that I'm computing the time evolution, so I'm really computing something like this. When will I get an n up here if I'm computing the time evolution? If the energy of the Baryons, if the mass of the Baryons scales like n. So that's the claim, that the mass of the Baryons scale like n. Now, it makes sense. So now we can see that we can also try to see that this picture should tell us that there is also a good large n limit, but we need to be more careful. So let's try to understand this n. What could this n be? It could be something like n times the energy of each quark. That would explain why it would scale like n, right? Plus n squared, which is the number of interactions, times the interaction between 2 quarks. But the interaction between these quarks, like we saw, is of order 1 over n. And so in total, all this would scale like n by the heuristic argument like this. And you see that this argument generalizes. If I had said I have a 3-body interaction, for example, between 3 quarks, it's the same story. You repeat this argument, you add the 3-body interaction, you know how small the 3-body interaction is. We can do it, let's do it. For example, the 3-body interaction, instead of 1 over n from 2 vertices, we get 1, 2, 3, 4 vertices. So a three-body interaction would be of type 1 over n squared. But it involves three bodies, so when I sum, I get n cubed. Okay, so order n. Right? I could do more. I could go here and I could put some loop to modify this interaction. Well, how does it change? It doesn't, because I have 2 1 over square root of n and 1 more loop of n. So same thing. So you easily convince yourself that I have n quarks and their interactions are very tiny, but there are many in a way that compensates so that in total I have n times something about the line. And so we learn that the quark is n q's, where each q interacts very weakly, but in many q's. Right? So I have a q that interacts very, very weakly with a sea of q's, but very, very weakly with each of them, but there are many. And so each q feels a mean field generated by all the other q's. It will field an effective interaction generated by all the other fields that will generate an effective potential for that q. Okay? What time is it? I don't want to go. Sorry? Half past 4. We are 1 hour in, so I will not go into the details of Hartwell treatment. So let's try to conclude now some things about the, I'll skip. So the next step Witten does is say, if we know this, he explains how to do something quantitative, namely how to find the wave function for the baryon constituents in the non-relativistic limit when the quarks are very heavy. I put n quarks with some potential between them, and he goes on and analyzes a bunch of cute things. Let's jump that part. So let's now analyze interactions. So here is the picture for a baryon. So we are learning. So we learned about Mesons. What are we learning about baryons? So baryons, their masses scale like n. Okay? And now we could ask what happens when I have a baryon and I scatter something against the baryon. For example, I scatter a meson, I put a meson here, and I want to see how this meson scatters with the baryon there. Right? So I put a meson close to a baryon. Well, it's easy to see what can happen. So what do we expect? Let's see what we expect. So this guy will interact with this guy. Now, to get some intuition, let's remember that this process is related by crossing symmetry to the process where I have two mesons annihilating and producing these two baryons. Right? I just flip and I see this process. Now, here, what do we see? We see that this process is the probability of creating each of these pairs of mesons is x, then this process would scale as something like x to the n to create n pairs. And so this process would be e to the minus n times c, to be exponentially small. In other words, it's very hard to scatter two light things and produce two very heavy things. It's a tunneling process. And tunneling processes are exponentially suppressed. Do you agree? Now, look at the energy of these mesons. The mesons have some light energy. Then this process can never happen. For this process to happen, this energy needs to be very big. I need to send two mesons at huge energy to produce the baryons. Do you agree? So this energy is big. Now, it means that this process, which is exponentially suppressed, relates by crossing symmetry to a process here where this momentum transfer is big. Indeed, this is very hard. And it's very hard because we are asking for the meson to hit this guy and shift it. But it's very tough to shift a baryon. The baryon is very heavy. So that's why it's exponentially small. However, there is a different possibility here. Here I don't need this energy to be very big. So when the momentum transfer is very big, that means that it's exponentially small, and that's fine. Because that means that the baryon is being back reacted by the meson. That's very hard to do. But there's another possibility, which is that the momentum transfer could be order 1. Could be very small. No, sorry, could be very small. 1 over n. Instead of order 1. And that would be the case where the meson just flies by and is deflected by the baryon, but the baryon is basically untouched. Then basically what we have is that we just have the pion going to a pion in the background of the baryon. The baryon is just producing a background and the pion is moving on that background. What about two baryons scattering against each other? Nothing is suppressed. In the same way that the constituents inside the baryon, it was important to sum them all to get some effective behavior. Two baryons is just twice the number of quarks. If between n quarks the interactions cannot be drawn, between 2 n quarks they can also not be drawn. So what will happen when I send the baryon against another baryon? The baryons move. When they get closer, I need all the interactions between everyone, and they interact and they deflect a little bit. And the energy of interaction that was important here between guys in the same baryon will be important between guys of the other baryon, and they will deflect. And so the S matrix for baryon-baryon to baryon-baryon will be order 1. And it will describe some kind of big object scattering with another big object, some kind of big object scattering and then moving to each other. Okay, so now we are ready to reach the pinnacle of the paper, which is the discussion. Let's summarize what can be concluded from all this. And the conclusion is good. The conclusion is the following. Is that we saw that the large M analysis led us to this pion Lagrangian. The pion Lagrangian has particles. Particles are excitations of the field when this field is small. The field is small, then I have small interactions between the fields. When I have Lagrangian, when I have a theory, which is a weakly coupled theory, one thing we can have is particles, they are small. But there's something else we can have, which are solitons. Solitons are big configurations of these pion fields. And these big configurations, if I now put some profiles for my fields, you see they have some action of order n. They have some energy of order n. And there are some big configurations that move classically, like gravity waves, and move and scatter and move with each other. And so the claim is that baryons are solitons. And that makes sense. You see that the mass of a soliton that we learn is something non-perturbatively 1 over the coupling. But what's the coupling? The coupling is 1 over m. For us, that's what we learned in the first part. So that's perfect. That's mass is being of order m.
But can you repeat the other argument you gave in terms of Lagrange? You comment about the Lagrange?
All I'm saying is that once you have a theory, you can have fields that are zero. The field can be 0 plus a small fluctuation, and that's what we call a particle. Or I could have some big solutions, I don't know, some transitions between a vacuum and another, for example.
Yeah.
And that I would call a soliton.
But why you would identify this solution with the baryon?
Because the baryons have the property that the mass is 1 over the coupling.
Only because of that, right?
That's the main reason. But also because of all these exponential scalings. That's exactly what you would expect if that was the case. You see what you could do here? You could treat these excitations as particles, or you turn on a background, and then on that background you could put Mesons propagating. That's exactly the picture we got here. You could also ask what's the probability of sending two small particles and producing some big solitons, and that will be exponentially small, and it will be given by a tunneling process where in the path integral I tunnel from one classical solution to another, and that will be exponentially small. So just large n, it has all the flavor of being able to, that leads us to believe that the picture should be that in the large n theory, we get the theory of Baryons that are weakly coupled, and that there's solitons and solitons, the Baryons are the solitons of this theory. So that's the punchline of the paper, which I think is really quite spectacular. Let me just see if I missed some point. But I think this is basically. Yeah, then he makes some analogy with other theories that are integrable or that are more easily solvable, for which there are solitons, and he points out that the analogy works very well. So, yeah, I think that's it. Let's stop. So we went a bit over time, but this was a big paper. I did not go much over time. 5 minutes over time for this paper, and I think it's justified. Okay, questions?
Okay, sorry, again. I thought that you concluded the propagator was exponential minus n because it's exponential energy. Is it correct?
Say again? I did not say the propagator is exponentially small. That I never. I said that the scattering of two mesons to produce two baryons is exponentially small. I also said that the scattering of baryon meson go to baryon meson with huge momentum transfer is exponentially small.
But why is it so? So is it because consequence of mass of baryon, right?
You can think because you need many couplings. You need at least n couplings. And each coupling is a small number. So you get small number to some big power. And so that's exponentially small. The other intuitive thing is that you need a small probe to have a big effect. When the momentum transfer is enough to create these two states, it means that you have enough energy to change the velocity of this guy. You start with some guy that, let's say, velocity equals 0. And now you want to change the momentum of this guy, but the momentum of this guy is n times the velocity, because the mass is n, basically, right? So to changing this velocity is really changing the momentum like crazy a lot, and the energy as well. So it's a very tough process.
Yeah. Okay.
So baryons are much heavier than mesons, and mesons in the presence of baryons behave as probes, unless we scatter very high energy, and then it's exponentially small process. Why it's exponentially small? Another way of saying it, because of what we saw in the very first paper we studied. Because there are so many states that could be produced that each of them better be exponentially small.
So the discussion about identifying the baryons as solitons, can you get anything? I don't understand. Can you get any intuition about them from the action or from writing the action like this, or it's completely?
Yeah, so you could ask. I don't know much about this subject. And this statement is probably something obvious. I think this is in the origin of what people call the Skern model and so on, where they try to make this precise. It's very possible that to try to say anything quantitative about this statement using the Pioneer engine, maybe you cannot truncate in the number of terms in the effective action. It's possible. I don't know, Andrea, do you know how to make use of the statement that the Pioneer is a soliton from the Carroll engine? It probably requires resumming everything. In the same way that, for example, let's remember a theory where solitons exist. It's sine-Gordon, right? Sine-Gordon is the potential is cosine, and you have these solitons, right? So we have sine-Gordon is the simplest possible theory, which has this soliton where the potential is cosine phi. What are particles? Particles are excitations where the field is 0, and then a small bump, and then this. And particles are very easy to see, because this potential is just 1 plus pi square over 2 plus dot dot dot. And so, around phi equals 0, this is just a massive scalar with mass 1, and and then there are interactions, phi 4, phi 6, and so on. Very easy. But how do I see a soliton? A soliton is like a transition between phi equals 0 and phi equals to 2 pi. That's another vacuum of the theory, right? Because the potential is periodic. I will never see it if I truncate it at some point in phi. I will need to resum everything to see the existence of this soliton going from 0 to 2 pi. So probably the same thing will be true here, I guess. But that's what you should tell me on Friday, because we are going out to find some beautiful papers that will compute the mass of the Baryons from effective field theory. So we have to randomly, and I forgot my computer. Can you open Mathematica? So we have to now randomly select the 4 students that will present.
I forget what you did exactly. I see you did like.
Can you open Mathematica? Okay. So let's do random sample. So remind me names of people, of the 5 people. So Egan, João, Rodrigo, Francisco, Leandro, you skipped the last 2 presentation classes. And you asked us to move schedules around and so on, and then you don't come. Not good. Okay, let's random sample 4. Where do I zoom in? Over here? No. Can you help me zooming in here? How do I zoom in the student edition? You cannot zoom in because they assume students have good eyesight. Okay, so you see, random sample 4. So let's see. Return. Oops. Typo. Okay, random sample. So first Francisco, then João, then Egan, then Rodrigo. So Leandro, you don't present this paper. So you will be presenting the Grossman paper. No, the Zomologic paper. Yeah. So then next week we do Zomologic paper on Yang-Baxter. And so Leandro will present Zomologic and who else? And then 3 people out of. Can you raise your hand? The ones that just make sure that we are still. And then out of the 4 of you, 3 people will present. Yeah. Maybe you should present for sure. But
I think it should be in this round.
Sorry?
I think it should be in this round because I was in the last cycle.
Anyway, everyone will present 3 times. So. Okay, so Francisco starts, then João, then Egan, then Rodrigo. And yeah, so you pick 4 papers that cite this paper and that are relevant and that are impactful and recent papers. So 20 minutes each. So let's do it on Friday and can we do Friday at 9:30 instead of 10?
Yes.
Is it okay? Okay, so Friday 9:30.
Meeting now or
So you can hear the Baryons, the Baryons fuse the background and the class.
Oh, for sure.
Yeah, it's high.
I'll check my emails somewhere.
You like to have a free party, so let's go back. Particle bounces all.
Okay.
Yeah, same story. Baryon like a wall, of the particles, right? Something very edge. If we put it there, see how the Meson
Yeah,
will go.
but Glueballs, they don't talk with any of them.
No, the global will also interact with the baryon in the same way. A baryon and the same story. This is a global and the same story.
Okay.
Replace pi by global with the same story.
So the Glueball doesn't interact with Meson.
No, that's not.
Glueball still interact with Meson.
Well, the Lagrangians will also have global terms, but also small interactions between globals and pi.
Okay, so small interaction means the exact logarithm.
Exactly. It's factorized, I don't know very well.
Should we think this?
And therefore, that's just factorization. But factorization works when you have order 1 operators. When the operators are order n inside, there's no factorization anymore.
Yeah, exactly.
And therefore, baryons are a bit more subtle than higher than
Yeah.
mesons and globals.
Yeah, and regarding the existence of the map, I think we need to prove something like that. We need to prove that
Argue.
yeah, but how do you exactly show it? You just argue like that.
No, you argue. It's a physicist proof. It's based on confinement plus diagram.
Yeah, diagram is clear, but why the diagram comes to this term?
What would you like to put there?
Yeah, I don't know, but if I don't know exactly what should be there, everything is possible. Right? I mean,
If you don't
if
know
you
what
were
to write, you can write that.
yeah, rigorously speaking, but that's, yeah, I mean, intuitively, of course, this should be such sums, but
And that's a paper about intuition.
okay.
But it's not a paper about axiomatic filter.
Okay.
We know that because since some of these computers are a good approximation to nature, do we know what the real expansion parameter in terms of 1/3 is?
Whether it is 1 over n or if it is 1 over 4 pi times n, like we said. That's a great question. That's a great question, and I should probably know. Good question. Yeah, it's a bit fun. Why wouldn't you do some one-loop computation, right? Some propagator, base square, planar, and one loop with some genus line and compare both. Let's see.
I think at that time it would be.
Maybe at the time, maybe one loop was tough.
I mean, papers are already 59 pages long, right? So, let's.
Maybe, probably no. But yeah. It's probably known for some quantities how good it is, and for some quantities not really. The simplest place to look would be pure glue. I have pure glue, and I want to compute mass of Glueballs, for example.
There are a few papers.
And then you compute them at large n, compute them at finite n, and see how good is large n, for example, for computing the mass of the Glueball at n equals 6.
There's a paper on that.
A bunch of papers studying that, the flux too, and so on.
But I'm not sure if he does.
Did you manage to read the full paper? It's nice, right?
Yeah.
It is, yeah.
Yeah, everything that
It's amazing.
really good page. But
Yeah, he's
Very right. Probably this is a all of nature. It's a good theory. All of the good theory. Right when the theory is a theory.
1/3 is equal to 1 over infinity. I love it.
Yeah, it's really.
and he's very thorough as well.
yeah, papers that written usually writes. Every paper that he writes is very good.
No, that's
Enjoyable too.
Yeah, it's not a huge surprise, but yeah, but it's always more impressive when it's a paper about real nature.
Yeah.
But
But that's not something that because
there are no examples. That's fine because we don't see too much of examples. Right? It's cool. draw some diagrams and see glue is more important than quartz. That's basically why we don't see exactly information.
Yeah, very interesting.
Amazing.
So, can you just go back very quickly to the argument about, I missed the argument about the masses, that the n factorizes and that doesn't change the mass. So I didn't.
Yeah, the statement that everything is of order n, there's no n dependence inside the a's are proportional to square root of n, but otherwise the masses have no n dependence. Right?
I mean, didn't you use this to? So the thing is that the correlation function is the power of n, and the a's are square root of n. That's basically that's enough to say that n, the masses don't have anything. So
Yeah, it's the statement that the correlation function is equal. The first step to say that this is n times the function of k squared.
Oh.
This follows from planarity, right? And now you say, what is this f? Well, this f will have poles at the position of the masses.
Okay.
Because there is no n inside here, the masses cannot have n. So large n limits, you do it on the lattice, you should find a good limit for the masses of Baryons and Glueballs. But Baryons, you need to divide by n. You divide by n, and then they have a good limit as well.
So, for the paper, I was looking for these last few days, and I thought about talking on it's one by John and Leonard Baryons and Baryons.
Good idea. Good idea.
So the idea was to cover, so the paper is huge, but the idea was to show how to extract the constraints from these large entities.
That's a great paper. Just make sure that, just practice.
Yeah.
Pick a good amount and so on.
Try to take into consideration.
Yeah. Yeah, but that's a good shot.
Okay.
It's one topic of research that people are interested in trying to know in history level, how can we constrain these coefficients using good stuff like that.
See you on Friday.
Oh yeah? Okay.
Sorry, it's just a sort of basic question about, so it's important that the expansion parameter is g over root n, right? Because if you didn't have the square root of n, then on the expansion coupling, then your 2-point function becomes proportional to n, right? And then
Yeah, but why don't you choose the coupling to scale like that to have a good limit?
yeah, okay, because then you
That's
can.
the definition of your theory to make sure you have a good limit. There is something that people understood after, which is you could choose the coupling to be whatever you want, but it doesn't matter because later there is RG and the coupling flows. And if you chose the wrong coupling, the coupling will flow to this.
Okay, that's it.
So it doesn't matter.
Okay, that's true.
But that is the way to scale to have a good limit. And then it's preserved by RG. If you choose something wrong, RG will put it in
It's
the chest.
so it's a fixed point in the